So, hi everyone. I'm Abderrahman Guelzim, a PhD student at Centre des Matériaux of Mines Paris School. And I'm studying the fatigue crack deviation in thick rolled plates of the 2050 T84 aluminum alloy. And I'm working under the supervision of Vincent Maurel from the Mines Paris School, Vincent Chiaruttini from the Dionere, the French Aerospace Lab, and Érembert Nizery from the Constellium Technology Center, which is funding this thesis. Today, I'm going to focus on the role of T-stress on the fatigue crack deviation. Okay, so the 2050 is used in aircraft structure when where multifunctional materials and lighter materials are needed to meet the environmental challenges. So it's an aluminum copper lithium alloy, and the addition of about 1% of lithium increase the material performances in comparison with incumbent products, and it's obtained by the hot rolling process. And for rolled plates, there is a specific coordinate system. So we have L for the rolling direction, T for the long transverse direction, and S for the through thickness direction. And as we can see, this process have an impact on the microstructure. So we have a textured material with grains elongated towards the rolling direction. Okay. So this process is also known to introduce mechanical anisotropy. So in order to identify the mechanical behavior of this material, smooth tensile specimens have been sampled in the SL plane of the plates from different orientations. And below I have plotted the stress strain curves, and as we can see, the elastic domain remains isotropic, and the anisotropy is only in the elastoplastic domain. Okay. So on the right, I have plotted as a function of the sampling angle, the ultimate tensile stresses, and the elongations at failure in blue. So as we can see, the stress anisotropy is low in comparison with the elongation and at failure anisotropy. So as we can see, in intermediate directions, there is a loss of ductility. And this elongation at failure suggests a pronounced toughness anisotropy. And now I'm going to present the crack deviation phenomenon. So this time we have sampled compact tension specimens, always in GLS plane of the plates. And as we can see, for the specimen CT 0 degree, where the notch is aligned with the rolling direction, we have an expected path, which is a crack that is propagating perpendicularly to the loading direction. However, when the notch describes an angle with the rolling direction, we can see that the crack tends to realign with the rolling direction despite an unfavorable loading conditions. And if we look closer in the CT 90 degree specimen, before deviation, the crack is transgranular and it becomes intergranular after deviation. And these two paths are corresponding to multi-axial load. However, our specimen is uniaxially loaded. So which are the mechanical parameters that are driving the crack deviation? And in other words, how could we consider the multi-axiality? So this is why we are interested in the T-stress. So when we see the Williams expansion describing the stress field at the crack tip, we find singular terms and regular terms. So the singular terms are the well-known stress intensity factors. So for a 2D problem, for instance, we have K1 and K2 for respectively the mode 1 and the mode 2. And the first regular term is the so-called T-stress. So the T-stress is a stress acting along the x-axis. In the figure below, it's a representation of a crack tip, and the circled area represents the zone dominated by the stress intensity factors. And far from this zone, we have SXX and SYY, which are the stress components respectively along the x-axis and y-axis. And T-stress is computed as the difference between SYY and SXX. So this is how T-stress take into account the multi-axiality of the problem. And we can see how the T-stress have an impact on the crack size, the size and the shape of the plastic zone at the crack tip. So for positive T-stress values, we have confined plasticity, while it's extended for negative T-stress values. And Köster and Rice finally established that crack paths are more stable for negative T-stress values. So, in order to investigate the role of T-stress, we have used several specimen geometries, allowing a wide range of T-stress values. And in this presentation, I will only present the results obtained from the compact tension specimens with positive T-stress values and the middle tension specimens with two sides that have negative T-stress values. And I will explain later why I have chosen two sides of empty specimens. So the tests were conducted under a constant load amplitude, and we have used an optical microscope to track the crack from a mirror polished face. And on the other side of the specimen, we have introduced a speckle pattern in order to measure the displacement field by digital image correlation. And now I'm presenting the results, so the crack paths obtained from MT and CT specimens sampled at 60 and 75 degrees from the rolling direction. So as we can see, in the MT specimens, the deviation is sharp angled and is associated with secondary cracks. While in the CT specimens, the deviation is smooth and progressive. And when the specimens are sampled with an angle of 90 degrees, which is commonly called the L-S loading configuration, we can see that we have two types of paths. So the first path in the CT specimens. So the first path is we have a progressive deviation with some secondary cracks, and the second type of path is in the second type of path, we have a sharp angled deviation with crack branching. And when we analyze the GIC residuals on the other face of the specimen, you can see that the branches are not necessarily through cracking the specimen thickness. So we can't find this secondary crack there, nor this branch, nor this branch. And this movie is a representation of actually, okay, sorry, please. Sure, take your time. So this movie is a presentation of a crack provocation of a path of type 2, and we can see that there are some branches that are emerging from the subsurface, and there is a lot of crack splitting and branching. So it's a quite satisfying movie. And we can see that we cannot understand all the crack growth mechanisms only from the surface analysis. This is why we have analyzed the fracture surfaces, and we observed the presence of secondary crack that are the deviated cracks that are going bigger and bigger until they coalesce and lead to the final deviation. Okay. So now let's go back to the empty specimens loaded in the L-S configuration. So in the empty specimens, I remind you that T-stress is negative. And as we can see, there was no crack deviation in the small empty specimen up to a stress intensity factor K equal to 30 MPa square root meter. And we couldn't reach a higher stress intensity factor without breaking the specimen. This is why we have used another empty specimen of a bigger size. And now we have obtained a very complex path, so we can see that the crack is zigzagging and is accompanied, is associated with a lot of secondary cracks, but there was no final deviation. And now I have plotted what I have called the K-dev, which is the K-max at deviation as a function of the sampling angle of the specimens. And as we can see, this parameter is predictive of the crack deviation despite some scatter for high angle values. And we can also see that this parameter, so the K-dev, is anisotropic and is increasing by the sampling angle. Also, by distinguishing the two types of paths, we can reduce this scatter. So we can talk about two different mechanisms, and we can also notice a T-stress effect for high angle values. So to conclude, in the empty specimens, no final crack deviation is observed in the L-S configuration for Kmax above 50 MPa square root meter. Negative T-stress values also delay crack deviation for near L-S configurations. These same negative T-stress values enhance the propensity to sharp angled crack path. And finally, sharp deviations are associated with an increased stress intensity factor at deviation as compared to smooth deviations. And all these results will help us to propose a crack propagation criterion taking into account the crack deviation. And thank you for listening.